Hello, my name is Sophia Bonser, and today I'm going to be going over my research on using a multi-step synthesis for the production of hydrogels with adhesive properties. In case you're unfamiliar with what a hydrogel is, it is a network of synthetic hydrophilic cross-linked polymers that have the unique capability of acting as both a solid and a gel at the same time. And then when they are exposed to external stimuli, they're able to actually switch between the two architectures. Hydrogels are very common in medicinal research for things such as wound care, wound dressing, tissue repair of burn victims, glues for bandages, and things of that nature. And this is because hydrogels are very similar to our natural tissue. The two focuses of this target hydrogel that we were making was one, the adhesive properties, which were inspired by 3,4-dihydroxyphenylalanine, also known as DOPA. This cross-linked polymer is found in marine mussels. It allows them to bind tightly to the metal surfaces of rocks found in the ocean, and then also just the adhesion of the feet of a gecko. So that was one of our focuses, and then the next focus was its sensitivity to UV light. So as I stated before, when exposed to external stimuli, they're allowed to switch between the two architectures. And so in this case, our external stimuli was UV light. And the reason for this is because when applying medicine to wound care, we would like the medicine to be entrapped inside the hydrogel to be applied to the wound, and then UV light applied to that hydrogel in order for it to switch its architecture, allow medicine to reach the wound, and then once enough medicine has reached the wound, the UV light is removed, it again switches our architecture and re-entraps the medicine. And so that was our goal for the second focus. As I said before, and as you can see in the title, this is a multi-step synthesis. So I'm going to quickly review the 3 steps, and then I'll go into what I've been doing. So figure 2 shows step 1 of the synthesis of these hydrogels, which is the synthesis of N,3,4-dihydroxyphenyl methacrylamide, which will from here on out be known as DMA. This is the monomer of the hydrogel, and this monomer is then used in step 2 to synthesize polydopamine methacrylamide and isopropyl coacrylamide. So this is the polymer that we are going to polymerize. So it's the backbone chain. And then the third step is the actual polymerization of the hydrogel and then the characterization of it. So my research is over step 1 and my attempts for step 1. As you can see in figure 2, the main reagent used is dopamine HCl, and our goal was for dopamine HCl to react with our methacrylic anhydride, but those are not the only reagents used. As you can see in our experimental design section, we also used sodium borate, sodium bicarbonate, distilled water, and argon. The argon was used for our degassing method using the Schlenk line, so it wasn't actually a part of the solution, but it was used to help the solution react. Figure 4 is an H-NMR spectra of N,3,4-dihydroxyphenyl methacrylamide. This is the correct H-NMR spectra, and then in figure 5 you can see our attempt and our results. As you can see, they are not the same. We were not successful in creating DMA. However, there are some similarities between the peaks, and there is a lot of noise in our H-NMR spectra, which we believe is due to a low frequency instrument, but we also believe that there was some error on our methods that allowed us to get this instead of the proper H-NMR spectra. And so going further, we have decided to reevaluate our degassing method because this is the most important step in our synthesis of DMA, because if we do not degas it properly, the dopamine HCl will just react with the water instead of the methacrylic anhydride, and then our reaction won't proceed. So we are going to reevaluate and perform a bubble test on the Schlenk line, and if that doesn't work, we will try a freeze pump thaw method, and then if that also doesn't work, we will try a different solvent instead of water. I would like to thank Dr. Lisse for allowing me to do this research, the Department of Chemistry, Physics, and Astronomy at Georgia College, and I would like to thank you for listening, and I look forward to hearing your questions.